All right, so let's get started. It's been a minute since we've gone through this new material. But this is an interesting topic, and you can really start to see the power of Laplace transforms. And it's particularly helpful when we look at AC circuits, because one of the things the power world is really worried about is the concept of switching transients when breakers open or breakers close. What kind of problems can arise in your system? And they tend to be less of an issue with inductive circuits, more with capacitive circuits, but we'll show the inductive one and we can talk a little bit about how you get the same sort of transients. And so we're going to mimic a simple circuit representing, a part of a utility system. And for some reason, a breaker opens as indicated by the switch, T equals 0. For whatever reason, the load disconnects, the customer didn't pay their bills, you're shutting them off, doesn't necessarily matter. But the idea is that when that switch opens, remember, there's a bunch of current I3 flowing down through that resistor. Well, this is the source, power source, right? This here is the inductance of the line. And that inductor says, I need to make sure that the current that was flowing before time t equals 0 is exactly the same as the current flowing after, just after time t equals 0. So this current here is still going to be a part of that, right? So you can see that I've still got I3 flowing in there, but I2 isn't changing because the same deal, right? Current can't instantaneously change in an inductor. So now what we have is I1 now has to have the residual current going through it, right? And what happens when we increase the current through a resistor? The voltage goes up, doesn't it? And depending on where the current is, I3, that voltage is an instantaneous change and it can spike pretty high. So that's the problem with real world circuits, right? When we have things that can or cannot instantaneously change, we can get real problems in our system as indicated here. So let's actually analyze our circuit. And again, since we're trying to look at a practical example of where this would occur, we're actually going to look at doing some sinusoidal or steady state AC circuit analysis. So we've already discussed everything over here. Let's go ahead now. And this is where I'll have to pause because everybody here has taken EET312 or is in it now. Okay. For those of you who didn't have AC circuits here, if you see 120 at an angle of 0, does that make everybody nervous? You've seen it before, Homa?
Yeah.
You've taken AC, is that what you said? Okay, so you know steady state phasor analysis with magnitudes and angles. Okay. Because I'm going to start to actually jump back into the time domain and people are going to be like, what's going on? But as long as people have seen it, they won't get super panicked about it. And I would imagine by now, John has definitely introduced the concept of phasors, right, in 312. So perfect. Okay. So we got some numbers here. We've got an initial voltage, and that's our output voltage. Anybody have any heartburn with this output voltage here being 120 volts and not here?
No.
Anybody okay with that? So what's that? Well, I'm just asking you the question. If I have 120 volts at an angle of 0 at V out, do you have any heartburn with me saying that that's that voltage versus the voltage at the generator, VG?
Not at steady state.
Not a steady state? You all are really advanced because all your circuit analysis to this point, I would have thought, would be you set your power supply to whatever voltage you want, right? If you want 120 volts, you set VG equal to 120. Isn't that what you've done in the past? You've had a circuit where you've looked at the voltage someplace in the circuit as being at 120 volts? That's typically what you've seen? Now everybody's second guessing themselves. I'm not challenging you. I just want you to think about it.
It makes sense because I mean at steady state, that inductor is going to be a short. They all share a node, so that should be the same
But
as
it's AC, so you'll never be in steady state, right?
true.
So nobody has a hard time with that?
So no, there's going to be impedance from that inductor then.
Yep. But does anybody have an issue that I'm calling V out or V0 equal to 120 at an angle of 0? I thought all of you have done your circuit analysis. Again, just to reiterate, you set your power supply to 120, and then you analyze the circuit. I'm telling you over here that there's some voltage out on the system that's going to be at 120. And now what I have to do, I have to adjust VG to be whatever voltage it needs to be to provide 120 volts. Is that
Sure.
typically what you've done?
No, but you can do it.
You certainly can do it, but have you done that?
Yes. Not in this class, but in others.
Luke, you have a question or?
That like at VRMS, or is that something?
That's RMS. Yep. We're in steady state. So that's RMS. Yep. So here's the answer. In the utility world, and I'm going to throw something from another class. In the utility world, who's the boss? The boss? Who dictates what happens in the system? The consumer. Why?
They're the one that wants the load.
Well, they have load.
They're the one that's paying for that.
They pay the bills, right? So they're
And
the
we're the ones-
customer.
And
What's
we're
that,
the
Arthur?
and we're the ones that are turning things on and off at will.
Right, but if you're connecting to a voltage, you have no idea what it is. You might be burning stuff out, right? So are you going to stay connected to that utility? Or are you going to find somebody else? So the consumer, and we're consumers, even in the utility world, which is a monopoly, they're required to provide the voltage that you expect within a pretty tight tolerance, usually plus or minus 3%. So when you're out in the real world, in the utility world, this is how you actually run the system. You set your voltage to your load to be as fixed as possible, and then the utilities and the generators have to monkey with their system as necessary, and they do it all the time to provide you at 120. Because if not, you're waving goodbye to the utility. You're not going to be paying to connect to it. You'll just go to Home Depot and get a portable generator or do something else. So to actually say this is way more common. It's always done in the utility world. It may not necessarily be on your cell phone, right? Because the cell phone is, you get a power supply, which is your battery, and you get that voltage, and then it decays. But there's no control over the battery unless you're charging it, right? Over here, there's all kinds of controls that I can do. All right, so now we're going to go ahead and figure out what our currents are in sinusoidal or steady state analysis. My V1 is just 120 divided by 12. So I got 10 at an angle of 0 amps. My I2 is 120 divided by my inductor, J41.1. That's 2.92 at an angle of minus 90, right? Because I've got the phase shift associated with it. And if you remember Eli the ice, that kind of checks off, right? Because what does Eli say about inductive circuits? Oh, breaking my heart.
Current lags.
Current lags the
voltage
in an inductive circuit.
I said no. Yeah.
No, he said.
I said voltage leads the current.
Yeah. That hurts my heart.
No, it
Austin,
lags.
tell him why that's wrong. No, he just said voltage leads the current in an inductor. Tell him why that's wrong.
Oh, you said current lags the voltage, but the voltage doesn't lead the current?
No.
Is it because it's at 0 degrees? And the fan is at negative degrees?
No. I'll give you the background, and then I'm just teasing Henry.
No,
Although you did take 422 already, right?
Yeah.
So you really have no excuse. I am disappointed. But in industry, when we talk about loads, we say that the load is either leading or lagging power factor. If Henry said leads and I say lag, which is correct? They're both the same, right? But he has to do it in terms of voltage. I'm doing it in terms of current. So if I was to think everybody uses lead and lag in terms of current, then he says it's leading, then I would say, hey, the current's leading the voltage. Is that right in an inductive circuit? No, it would not be. So we all have to be on the same page, which means what is current doing? Current has to lead or lag. Remember that? There's current 422 students in here that should have immediately corrected them, but I guess I wasn't harsh enough in that class. But the current lags the voltage, which it does, right? The voltage at an angle of 0, the current is 90 degrees behind, so that makes sense. And then our R3, again, this is the initial value. So 120 divided by 8 is 15 amps. So the sum of the three currents is 25.2 at an angle of minus 6.65. Now, here's what the generator owner has to do. They have to monkey with the voltage, again, to provide 120 volts. So I have to set the voltage up to 125, and then that minus 11.5, you actually don't necessarily set the angle up, but you just pick a reference, and then the angle goes from there. So now we got to go back to the time domain. And the time domain, my current I2 is 2.92. Where'd that square root of 2 come from? Is that a typo?
Mm-mm.
What does that mean? It's for RMS.
Yeah, you
Keep going.
multiply by the square root of 2 to go from your regular voltage to your RMS voltage.
Oh, so close. You multiply by the square root of 2 to go from RMS to peak voltage, right?
Yeah.
Not the other way around.
Yeah.
So yeah, I got to put the square root of 2 because what we do in our wall sockets is we have 120 volts, but in actuality, the voltage hits almost 170, right? That's the peak magnitude. So if you actually monitor the waveform, you wouldn't see 120, but like a couple times a cycle, but you would see 167 as the peak. So we have to add the square root of 2 in there, times the cosine. We're just going to pick a cosine wave. It could be a sine wave, but cosine usually is a little bit easier. 120 pi, which is 2 times f. We're assuming 60 hertz, right? Throw our pi in there, and then it's our t, which is just our time, because this is a sine wave or a cosine wave, minus 90 degrees for I2, and I3, I0, just convert it to peak and put our phase shift inside the cosine waveform. Now, we're going to go through and see what happens at time t equals 0. So we end up with cosine of minus 90. The cosine of 90 is 0. So we end up with 0 there. And then our I0, because we have a phase shift, we end up with 35.4 amps. So you see how we did steady state analysis, but now we need a specific time value. So those are our two initial currents. All right, so here's our circuit now, all written out. And this is our initial condition circuit, because now we want to go ahead and do circuit analysis here and then see how that circuit's going to change. So my initial voltage is 125 at an angle of minus 11.5. Our inductor is 2.65 Henry times S, right? Don't forget we have to do S times L. Our initial condition current through that inductor is L times I0. And then we have our resistor, which is our 12 ohm. And then we have our S times LA. Again, that's just the inductor circuit there. And we don't actually have to add any initial condition current because there is none, right? It's equal to 0. So we're going to use KCL, which says the sum of the currents into the node equals the sum of the currents out of the node. So we're going to say that, let's see, how do we do this? We have that current, and that current is our KCL, all currents going out. So we have V naught minus this voltage drop, minus this voltage drop, and then minus VG, right? So it's V out minus those voltage drops. And that is divided by S times L. And then we're going to add to that V out over S. So this voltage drop here. And then we're going to do this voltage, that current over there. And that's going to sum to equal to 0. Now we're going to do a lot of math behind the scenes, and we're going to end up with V out of S is going to be equal to the equation over there. And you can notice that I have my voltage here not written as an actual voltage, but as a function. I'm going to add that in because there's enough math that I need to do to make this work.
Can I ask you a quick question before you go on?
Yes.
How come you chose all the currents leaving that node rather than the current entering through the source, through the inductor, and through that source into the node? Just curious.
Yeah. So it's totally arbitrary. We
Okay.
can pick whatever direction we want. And as long as we are consistent, when I'm doing our circuit analysis, it's just an initial guess. If the current is in the wrong direction, if it's actually going into the node, then we would end up with a negative number or 180-degree phase shift in our result. So it doesn't change anything. It just is our initial guess. So it doesn't, you can go either way. Okay.
Okay.
All right. Now we're going to put our sine wave in, and our sine wave in the Laplace domain is 253 over S plus 1475 times pi. No, that's not that. That's actually in there. So when we do partial fraction expansion plus that, we end up with this expression over here. This is the decaying exponential. That is the natural response. And this is no decaying exponential. So that, in fact, is the forced response. All right. So the output has the two parts, the decaying or natural, and the non-decaying or the forced. So we go back into the time domain, and we see we have this expression here. This is what the voltage is going to be after any transients die out. This is the transient we get because we opened the resistor, took it out of the circuit, and now we've got way more current going through that resistor than we should. This is how the voltage is going to spike. And you can see it's going to spike 253 volts.
Almost double.
Yeah. Here's the peak value right here, 173. But it actually goes up to 253 on top of that. Just because we opened that we took the load away. So here is our system running along just before time t equals 0. And then boom, we open our breaker. Now the voltage, V out, instantaneously jumps to 425 volts. But that has a very short time constant, right? If you look at the time constant, 1,475 T. So you can see that decays very, very quickly. That's going to decay in less than 3 milliseconds. And then it goes to steady state. Goes from there.
Yeah, but that can still do some damage.
Absolutely. So one of the things you see now, if you go to Home Depot or Lowe's, you actually see whole home surge suppressors, right? You put them on your breaker box. You can buy like a dual pole breaker, and it is intended for exactly this condition. When you have spikes that are passed through the transformer into your house, you can go ahead and get that. Now, that's a little bit of a joke because the transformer that feeds your house actually is a spike preventive measure anyway, right? Because you can't get instantaneous changes in current, so you're really not going to express the voltage all that much, but it doesn't hurt to add certain levels of protection as well. But if you're out on the system and you're above the transformers, you can easily get really crazy high voltages on your system.
Oh, I bet.
So
Now, that's
go ahead.
the whole home surge protector is a big capacitor, isn't it?
No.
No. Okay.
Great question. So if I wanted to modify the circuit and protect the circuit from surges, normally what you do what's that?
The Zener diode.
A Zener diode,
Okay.
right? You'd actually have it, you'd have to have it in both directions. Because it's AC, right?
Exactly.
But a Zener diode, and actually, I think you would actually use what's called a metal oxide varistor that protects in both directions. And so once the voltage goes above its threshold, where it starts to conduct in the reverse bias region, it will not do anything until it goes ahead and starts to conduct. So the surge suppressors in your house, definitely not a capacitor.
Hmm.
It's going to be just a device like this.
Well, that's even simpler than I thought it would be.
Yep. All it is just some semiconductor material. So like a voltage regulator, if you buy, an LM317, it's kind of like how an LM317 works, right? Once you get about 15 volt or 17 volts, they go ahead and start to conduct. I mean, those are a little more sophisticated than that, but this is just for high surge suppression. Those are really good job. And the utility world, they have all kinds of surge suppressors out on the system. So they're just called arresters. They're called surge arresters. And they're usually for lightning hits, but they will protect for switching transients if they're set up in the right place. Okay. Questions on how to apply this stuff practically? Because if you really like to look at this stuff, there's a class called, not a class offered here, but there's class on transients. There's a book, and I actually have it, and it's a classic book, and I don't know if they've even replaced it. It still works, but it's a transients book, and the whole thing is doing all the analysis in the Laplace domain. That's all they do. They just do Laplace, 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 and show you how to do it with that to analyze different systems, but far more complicated systems than what we've been showing you. Okay. Questions on that? Yeah, so the question is, do all parts of the system have the Zener on it so that they will be protected? They may. It depends on how much effort the utility has put into protecting their system. So they're obligated to provide, nominal voltage plus or minus 5%, but they don't claim that they won't protect you, that there may not be switching transients that would be a problem because it's not that common that would cause an issue to loads. But if you're out on the system and you have some very sensitive equipment, then you would be obligated to do it on yourself. And the only thing they would typically do is they'd have a surge arrestor on the line, and mostly that's for lightning protection. So it's set like if you take the nominal voltage and you multiply it by 120%, that's typically how high they would get before they start to conduct. At your house, then, 120% of the nominal voltage might be too much to protect some of the sensitive semiconductors, right, that you have. So those might be a different scenario, but you don't see a lot of stuff other than people trying to worry about switching transients. And so if you were to go to Orrington, they have a cap bank that it's a series, they have 2 series cap banks, and they can take those out of service. And what they do is they actually have a path around the cap bank that has essentially a Zener diode that protects it. So when you open up the breakers, the voltage tries to spike for one reason or another, and then it will just discharge the capacitor slowly. So you have to add a higher level of sophistication. All right, last topic for this Laplace stuff is to do things in terms of transforms. So we kind of did it a little bit over here. You'll notice we had VG of S in the equation for the output voltage. So a transform analysis is when you take an input and you run it through the system and you get an output. Another way to say that is the input is transformed to the output by the circuit or by my set of equations that I've written to model how that system performs. So transform analysis is really good if you don't necessarily care what the input is, but you want to see how the system might respond to various types of inputs. Because in some cases, you don't necessarily know what the input is. So that is the easier way, the more generic way to do it. And you can come up with some real generic equations for your system. All right. So almost all real world systems, if they can vary in the time domain, are going to be modeled with differential equations, right? Because everything's got some capacitance or inductance or something that represents that. And we'll see an example towards the end of the chapter where we can actually model a tank as a capacitor. So because we have differential equations, we have more complicated math to do, right? To solve, to get results. But we have this new fancy tool. So let's go ahead and convert everything to the Laplace domain before we do any of our circuit analysis. And then we can just represent each individual block. Why do you think we want to represent things as a block? Well, I'm really good at looking at a resistor and an inductive circuit, or a resistor and capacitive circuit, or an inductive and capacitive circuit. But if I take a look at a circuit that might have 30 resistors, 60 inductors, and 22 capacitors, now I've got to do a lot of circuit analysis to go ahead and figure out what the output is going to be based on an input. So it's far more complicated to do that. So what would be easier if I could break the circuit up into smaller pieces that I can maybe do single voltage divider or current divider and get the output, then it's far easier for me to figure out the system. And so I'm going to take a snapshot of a small part of the system, do whatever analysis I need to get the output based on the input, and then I'll move to the next part, and then the next part, and then the next part. And at the end, I will combine those all into getting one representation of a system. That's what people do, mechanical engineers do in the real world, because I can model a valve really easily. But if I have a valve and a tank and some pipe and an orifice and another tank, and I have all these different things in the system, to figure out what the output is going to be very difficult. So I break each part down into more manageable parts, and then I put them in what we call a cascade, and then we add them together and make sense. This only works if interstage loading is pretty small. And what I mean by that, if I do a voltage divider circuit on one part of the circuit, and then I want to do a voltage divider on another part of the circuit, something like this, what I want to do is break that up into these two parts and then figure out what V out is in each of those cases. So this is V out 1 and V out 2, and then put that together to get an overall transfer function for V out 2 over V in. But depending on these resistor sizes in here, I can get my results skewed, right? Because I know the voltage divider over here is not going to be 100% accurate because I've taken out that second stage. So what is the best way to go ahead and minimize interstage loading? I obviously can't physically separate them, right? Because I have to have some electrical connection between the two. So or what devices can I use that doesn't really change my circuit all that much, but will result in negligible interstage loading? I wonder if there's a device that has a super high input impedance so that when I tack it on to V out 1, it doesn't change the results at all. Its input impedance is so darn high, it doesn't have any impact. And then I want to connect it to the second part of the circuit. And so again, I don't want to have it have any input. So I've got to have a really low output from that device that I'm putting in there, really low output impedance, so I can ignore the fact that I'm adding a new device. What device would have a really high input impedance and a really low output impedance? Can you think of one? Luke? Yeah, just an op amp, right? Isn't the definition of an op amp? Like, isn't that how you analyze an op amp circuit? Let's see if we got our thinking caps on here. Let's see.
Right. I minus and I plus equals 0.
Say that again.
I minus and I plus equals 0.
I minus and I plus. Yes, you're on the right track.
Yep.
All right. You all are masters to know right off the top of your head that V out over V in equals negative R2 over R1, right?
Yep.
Everybody agree with that? Anybody not agree with it? Not a lot of yeses. Do we agree or do we not agree? Great. Prove it. I'll give you 3 minutes to prove it. And if you don't do this, I'm going to tell John, right? You've all completed 342 or an electronics class. This is 241. And home, I'm sure you've done electronics down there. This is an ideal op amp. I'll make it easy for you. I'm certain John has done this derivation. And Adam or Andy at SMCC probably has done this derivation. I don't know about Arthur and ECE, what they've done, but I'm sure if you've taken electronics there, they've definitely done the basic op amp.
Oh yes, no, we've done these. You can do nodal analysis and come up with it.
Yeah, you definitely want to do nodal analysis. That's the easiest way to solve for this.
Yep. Yeah, you're just limited by whatever the rail to rail voltage is going into it.
Yeah. So we'll give me a second. We'll talk about that in a little bit, Arthur. One more minute. All right. Who can prove it to me? Don't all jump at once. Answer the question. Shall I go see if John is here and he can give you the glare? All right. Ideal op amp. There are two conditions for an ideal op amp. Rn equals infinity. This is just to do our analysis, right? And the open loop gain is equal to infinity, right? For an ideal op amp. With those two conditions, if my internal open loop gain here is infinite, my output voltage is going to be equal to my open loop gain, just basically, times the difference in voltage, right? How do I make sure that this voltage does not get to be infinitely high, considering the fact that this is almost infinity? Doesn't this voltage essentially need to be zero or darn close to zero as possible so that it doesn't blow to infinity? So the difference in voltage between those two has to be equal to essentially zero. which means the voltage here, we'll call that equal to 0. And if that voltage is equal to 0, doesn't that mean that that's also a ground potential as well?
Sure is.
If there's no potential difference between the plus and the minus terminal, and the plus is connected to ground, then doesn't that mean that the minus also has to be not connected to ground necessarily, but at 0 volts? So isn't this current here, I in, equal to V in divided by R1?
Mm-hmm.
Because V in minus 0 is just V in, right? That's the voltage drop across the resistor. So it's just V in divided by R1. Now we have to use the second condition, which says Rn equals infinity. Because Rn equals infinity, how much current goes in there?
None.
0. So Kirchhoff's current law tells me since there's no current going in there, all that current has to go that way, right?
Yep.
So now I want to write an equation there. So I have 0 minus V out divided by R2 has got to equal I in, doesn't it?
Mm-hmm.
All that current is going into that node. Then I can solve for the current just by taking the voltage drop across the resistor and divided by the resistance. So V in divided by R1 has got to be equal to negative V out over R2. And with some fancy dancy algebra, by that, again, not getting a lot of enthusiasm. Is this not familiar?
I don't know.
But you don't remember seeing this? I mean, familiar, but it's been
We've seen a lot of them.
okay. So this isn't new or
Nope.
confusing or anything like that, because this is something, if you use op amps, it's kind of important that you at least do the basic op amp one to see what happens. But for us, it's so important because the fact that it has an infinite input impedance and then one other one that we take advantage of, the output impedance is 0, then we can take advantage of that. Now, Arthur mentioned one thing too, right? He said, as long as you don't go to the rails that he's talking about is the op amp has to be powered by, let's say, plus or minus 12 volts. So as long as you're not driving the output into saturation, which is like 11 plus or minus 11.3 volts. So if you're as long as you're within that range, then these hold true. If you're starting to try to drive it to 13 volts or even 12 volts,
Won't
none
do
of
it.
this stuff holds true because it's not operating as an op amp anymore. It's operating as just a saturated device that can't keep up with what you're trying to have it do.
That's when you get clipping of a waveform.
Exactly. You
Yep.
clip your waveform, or you just peg if it's a DC and you just stay at the rails.
We did those in ECE 214. We did integrating and differentiating off amps too.
Well, perfect. Because now
Ah, there it is.
we can do this. I'll give you 3 minutes. Prove this to me. Now I hope you see why it's so important to do Laplace. to prove this one would be very difficult without taking advantage of Laplace. Anybody got it? Still need time? Or will all the time in the world not make a difference? You want me to wait a little longer, or do you want me to go ahead and put it up? Go for it? Okay. So because I have this really simple tool that converts integrals and derivatives to multiplication or division, I'm just going to go ahead and immediately convert that to the Laplace domain. Because I just treat those capacitors as resistors. So I in, and I'll use capital I in because we're in the Laplace domain, is equal to V in minus 0 divided by 1 over SC, right? That's what the resistance equals. And that's going to be equal to 0 minus V out divided by RF, right? Not right? So negative, let me just go ahead and put V out over here equals negative RF times V in divided by 1 over SC. V out over V in is equal to negative RF divided by 1 over SC, which is negative RFC times S. Exactly what we have here. Okay? Now, help me out again. When we multiply S in the Laplace domain, what mathematical property is that again? I can't remember. Multiplication by S in the Laplace domain is equivalent to blank in the time domain. Multiplication by S in the Laplace domain is equivalent to blank in the time domain. Differentiation, right? When we multiply by S in the Laplace domain, it is exactly the same thing as taking the derivative in the time domain. So because I'm multiplying, or will be multiplying whatever input signal I get by S, I'm taking the derivative. I also am inverting it and multiplying by C times R. Well, if I make C 1 microfarad and R 1 mega ohm, then C times R equal 1, right? So I can take out any fact that there's a gain multiplier. How do I get rid of the negative sign? make those the same resistor value, right? Negative RF over RI, when RI equals RF is just -1. So that negative here gets canceled out and you no longer have an inverted circuit. So you can build a differentiator, a real world differentiator with just an op amp, a resistor, and a capacitor. The problem with that though is this derivative, right? This is going to take derivatives of whatever it has. So if you have noise coming in, like some high frequency stuff that gets picked up, that's going to differentiate and your output is going to be bouncing all over it as well. So sometimes what you'll see on here is for differentiators, you'll actually have like a pass band or a reject filter, kind of annoying. And then that's going to go ahead and bypass any of the high frequency stuff so it doesn't get amplified.
That's terrible.
I don't know if you can hear the noise in the background, but it sounds like the building's going to explode.
Oh, no.
Well, there's just some rattling in the pipe, so
Well, that's not good.
sounds like they got some water hammer in the system. So
Ooh.
it's starting to speed up. Maybe it's going to stop.
The water hammer is kind of analogous to an inductor.
Sort of. Yeah.
When you slam the valve closed, I mean, you get a surge of pressure buildup, kind of like when
you get a surge of pressure, but the thing about a valve slamming closed is the water stops, where the inductor says, no, it's got to keep going.
Yeah.
Right. So the pressure builds up, but yeah.
Yeah. Well, because
the
the inductor doesn't want to stop flowing current.
Right.
It wants to stay the same. It would be happy if it was just the same rate.
So maybe that's a better way to say it. It's not the valve, but maybe the pipe that is feeding the valve. Once it shuts off, it opens a switch, is what the valve is.
Yep.
And that pipe that has that flow, the flow still needs to continue because it has momentum, right?
Exactly.
It can't go anywhere, so the pressure builds. So I would say that the valve is the switch.
The valve is the switch. That's exactly what I meant. Yeah, sorry.
Okay. We're on the same wavelength. And the pipe is the inductor.
Yep.
So thank you. You just gave me another analogy right now. A long length of pipe in a hydraulic system is modeled as an inductor and a resistor, right? Because depending on the size of the pipe, it'll add some resistance to the flow. But if it's a really giant pipe, it might not add much resistance. But if it's got a small orifice or something like that, where it's actually kind of restricting the flow, then you can actually get that.
A deliberately placed orifice would be like a resistor.
It's exactly like a resistor. Yep.
Yeah.
Because why? An orifice is trying to limit the flow of water, resist the flow of water. And when you have an orifice in there, it takes the pressure that's behind, that's jacked up. And on the other side, the pressure drops.
Yep.
Because you're letting less water through, just like the case of voltage.
But if it oscillates,
what's that?
Yeah. But if it oscillates, it's still going to oscillate a little bit below the orifice too, just like it would after the resistor.
Yes.
Yeah.
Well, here's the interesting thing about an orifice. An orifice, anytime you have something that drops the pressure, that has to take energy out of the system, which means it generates heat. So if you go to a pressure reducing valve, which is the most common one you see, and it's just got water going through it, you put your hand on it, it's actually pretty warm. Yep. Because all that pressure drop means you have to take energy out of the system, and that gets transferred into heat, right? It's energy going through. You have energy here, and then less energy over here because the pressure is lower, but the flow is, let's say, approximately the same. So you actually have to lose energy in the valve. And so that's why pressure reducing valves are like millions of dollars, because they have to be able to take a lot of damage and take a lot of heat and not get damaged.
They take a lot of abuse.
Yes. When you drop the pressure, right? It's not a transformer. You're restricting the flow, typically.
But I'm thinking, if you're restricting the flow, wouldn't you get less flow and more pressure? Like an orifice?
But we're talking on the side of an orifice, you have two different pressures, right? One over here and one over here.
Mm-hmm.
So upstream, where you have more flow, the pressure is going to be higher than downstream.
Just like on one side of the resistor, there's more voltage than on the other.
Well, it's yes. If you could measure the pressure on one side or measure the voltage, it's going to be lower on the high flow side than on the low flow side, just like in the case of a resistor. But the flow should be the same, right? Because if you think about it, you've got a lot of flow, but you can't just keep putting, water in there. At some point, the pipe is going to build up as much water as you can get, so you can't get any more flow. So the flow is going to be the same. Otherwise, again, it's just going to keep overfilling the pipe. So at some point, once the flow gets consistent, now you just have a pressure drop, and that's how those systems work. I worked when I was designing power plants. One of the things we had is they had these flow water adjustment valves, which would control the amount of flow water, and they were like $2 million valves because they had a lot of flow, but they would run at 800 degrees and not get damaged. Really, really high pressure.
How big are we talking about?
It's probably the size of this desk assembly. So maybe, was that 6 feet by 4 feet by 3 feet ish?
Underwhelming for that much money.
Yeah, it could be, but the thing is, you have really elegant metals, really powerful, fancy metals that can reject that. So these are not something that, you go to Home Depot and it's not a brass valve, let's just say that. So. All right, so we'll switch things around just a wee bit, and now we will build an integrator circuit. And the only thing we did is swap the capacitor and resistor positions. So our current in is equal to Vin divided by R in. And that's going to be equal to our current out, negative V out, divided by 1 over SC, right? So positive V out is equal to negative 1 over SC times Vn over Rn. And V out over Vn is going to be equal to negative 1 over Rn C times S. What mathematical property is equivalent to, what mathematical property in the time domain is equivalent to dividing by S in the Laplace domain? You all remember? Just an integrator, right? So dividing by S in the time Laplace domain is exactly the same thing as taking the integral in the time domain. So you built an integrator here. Now, this is where you're going to be careful, because if you have any offset across these terminals, let's say you're not connected at all, this is Vn, and it's just floating in the air. If you have any DC offset in those two terminals, you're going to get some integration, right? You're going to get a voltage that builds up across it. That's what the equivalent of integration is. So you have to use very, very, very special op amps to do that. They're called chopper stabilized op amps. And how did we used to model systems in the real world when we didn't have computers? We had computers, but they're called analog computers. And let's see if I can go here and zoom in. That was how you used to simulate systems. You had, and it's hard to tell because you can't really zoom in, but you had a bunch of connecting points where you could tap in, you could run wires to, and you could connect integrators, you can connect differentiators, you can do all that, and then connect everything through there, and then you would power it up, and then you would see how your system would respond. My very first company I worked at as a full-time, quote unquote, permanent employee was a company that was in Alexandria, Virginia. And I remember walking into the lobby. It was a beautiful lobby. And in the back, they had like a little cubby, and they had an analog computer that simulated some sort of a control system on a submarine. I wonder if they actually have that picture still up. Let me see if there's any images. Probably not. It's not like that, that's for sure. I might not be able to see it. If this is the lobby, it definitely does not look like that when I was there. I don't think that that's it either. This is an engineering company, so they don't have a ton of, whoops, I stopped sharing. Sorry about that. Yeah, I don't see it. Sorry, folks, but whenever I used to walk in or I had to take the elevator in, they had an analog computer just kind of sitting there, so it was kind of cool. And the reason why I like covering op amps, am I not sharing my screen? I thought I was. The reason why I like including op amps, whoops, is because when I took the PE back in 1997, how many of you were born after 1997?
All of them.
All of you? Fair enough.
Not
And I
me.
remember taking the PE in Virginia, and one of the things that they did to make it seem like we were so smart was they replaced this with a device, and that device had a curve characteristic that did something like, whoops, like this. So it wasn't a linear feedback device, but all you had to do was say, oh, here's the current, here's the voltage. It was like really almost easier to look at a curve to do it. And so if you have any comfort at all with op amps, at least back at the day, that was an easy 10-point question for the PE. All right, so now we've got op amps and kind of hopefully a little bit of review for op amp. Let's finish up the section by doing a transform for a series RLC circuit. Okay, this we can't use the Y of T equations for first order circuits. We got to use the RLC. Well, because we have an inductor and a capacitor, we've got to use Laplace to do this. So the very first thing we're going to do is take it to the Laplace domain, because again, I don't want to solve or write any differential equations. I want to make it easy on myself. So here is the circuit converted into the Laplace domain. So we have an input voltage. Our current is in both of those in the Laplace domain. I have an R, an SL, and a 1 over SC. Now I just do a KVL loop. Sum of the voltage drops around a closed loop equals 0. Doesn't matter if I'm in the time domain or the Laplace domain. So you can see I summed the voltages there, assuming that these were plus to minus in the direction shown. And then my transfer function I'm looking for is the current flow through the system. That's our quote unquote output based on an input voltage. So that's going to be 1 over R plus SL plus 1 over SC. I'm going to go ahead and make the system look a little bit fancier. Instead of having fractions and fractions, I'm going to get rid of the fractions. And so I put everything under a common denominator, which, let's see. I just basically, I multiplied everything by SC. Did I forget that over here? I think I did, right? If I go up over here, if I put everything under a common denominator of SC, yeah, so I have to modify this a little bit. Oops. Let me modify this. All right, so this whole thing, right, has to be, so I have this, I have 1 over SC, and so I multiply everything by SC, so I have to put S times C up over here. And I have an S times C over here. Which means that that will cancel out. Okay. Yeah. Didn't you know there's an equation editor in PowerPoint? In all the Office products, there's equation editor.
Really?
Yeah, so I'll just show you really quickly. But if you insert an object, where is it? Not symbols.
There should be insert equation there somewhere. It should be next to symbol. It
Yeah,
usually
I
is.
don't see it. Maybe I got to go to the down
Oh,
arrow.
no. Hit the down arrow under symbols and it should pop up.
Okay, yes. So you can insert an equation right there. And you can make it do fractions, you can do integrals, you can do matrices, you can do all that stuff. 5 to 10 years ago, this wasn't available from Microsoft. So I used to use a product called MathType, but now this comes free. So remember how I keep telling you all, you should have all your equations when you submit a formal lab write-ups, really beautiful looking.
Yep.
That's how you make them look beautiful.
Yeah, we had to do that with EE.
EET?
Yeah, ECE24, because that was a writing, that was counted as your writing and major intensive. So
I'm
yeah.
shocked because I thought in ECE they wanted you to use LaTeX or
Oh, we
LaTeX,
did for the final one we did.
which is really funny
Yeah.
because nobody in industry uses LaTeX or LaTeX. Maybe if you are at PhD level where you're doing stuff, but Word
Yeah.
has gotten so flexible in what you can do. I've never written a report in LaTeX or LaTeX or wherever I just said it. And I would be curious to ask those teachers, do they actually write things in LaTeX or LaTeX? So,
I don't know, but they made us do it.
no, I know. I'm just saying that's kind of antiquated to how to do things. Like, why not just use what everybody
Yeah.
else is?
It's a hard way of making a PDF, is all it is.
Yes, where Word it's kind of built in.
Yeah. Yeah, but I mean I believe that if you were to look at a PDF document, the backbone of it is latex. If I
Oh,
remember
really? That's what they use to
Yeah,
make it work?
I believe it is. I could be wrong on that, but I believe that was kind of the backbone of it.
Well, I have no way of knowing either way, so I'll
Yeah.
I'll I'll defer to you. That's no problem. So yeah, so here is our circuit, and basically we have a second order circuit where we have to do quadratic equation and do all that stuff that we need to do. And it's going to be either two exponentials, decaying exponentials, one decaying exponential with potentially a ramp, right? If you have repeating roots, or you're going to end up with a complex sinusoidal waveform output. So that's how you can get oscillatory response in an RLC circuit, right? You can energize an RLC circuit with a DC source, and if you monitor the current, you can get some oscillation. We'll talk about that more in detail next semester. So here's the tank system that I talked about, and we're going to see how that's modeled as a capacitor. So we have the height of a tank, and sometimes that H term is not called height, it's called head. So the head of the water, which is like how high the water is over an output port. They talk about head more in like hydroelectric facilities. You've got water filling in, and then you've got an orifice or valve with an orifice that's limiting the flow out. Isn't that exactly like a capacitor? I'm dumping energy into the device. In this case, it's a tank. The flow out of it is restricted or it's completely closed off. And what happens? The level in the tank increases, right? Which means the pressure at the bottom of the tank, because water weighs something, right? If you go to the bottom of the ocean, it's immense pressure, where if you're at sea level, it's whatever, the normal pressure is. So you can see just by putting water in the tank, you're going to build up pressure. Or in the case of capacitors, you're dumping in electrons and you're building up voltage. Once you start to pull more electrons out, because either the voltage gets to a high enough point that the flow of electrons going out matches the flow of electrons or the flow of water going in, then the tank level equalizes. If you want to take more electrons out, what do? I crack the valve open more. Isn't it the same thing as decreasing the resistance seen by that system? So this right over here is a variable resistor. And this is a capacitor. So if you talk to our mechanical engineering friends and we're trying to model the system, a tank system, tank is just a capacitor. If the length of pipe that goes to the valve is short enough, then we can just include the resistance. Otherwise, if this gets to be really long, then we actually need to treat that as an inductor. Okay? Oops. So here's the system, right? Because we have a resistor and a capacitor, that's just a first order circuit. So the flow out of the system based on the flow in on the system has a time constant. So you have this resistive value. What's rho times G? Rho, we think about it as resistivity, but in a water system, it's the specific gravity of the water. So if you want to get the pressure of something, you can take the specific gravity or specific density, I should say, multiply it by G, which is just gravity, right? It's acceleration. Then you have the area of the tank, and then you have the time constant of the system. That's all it is, just a first order circuit. And that is it for Laplace, which means you're ready for your next test. Which has to be not this Friday, not next Friday, because next Friday is break. It'll be the Friday after. So 2 weeks from this Friday will be your third test. It's going to cover everything in this module, Laplace, everything up to and before that as well will count.
Oh, great. Might as well just throw mine in the trash can.
Well, it won't be specifically looking at that, but I mean, you got to know how to do KVL, KCL, you should be able to do all that stuff. That's why we spend so much time reviewing it. So it's like the base level stuff that we need to advance our understanding. Yes, sir.
Is this coming Friday, is that going to be a test review then?
No, so the test review, so a week from today, well, you can decide. So we have Thursday's class, Tuesday's class, then Tuesday and Thursday class. So we have 4 classes in between now and then. You can decide when you want to do a test review. So a week from today, I won't be here. So I'll do a class. I'll either record a class or I'll do a live class. It just depends on my setup. But so next Tuesday, we won't have an in-person class, but it may be live. I'm not sure. I'll just work that out. You can decide when you want to do your test review. Do you want to do it before Thanksgiving? I would suggest doing it after Thanksgiving. So Tuesday after they get back would be fine. So basically 2 weeks from today.
What
Yeah.
then,
Go ahead.
what then is this Friday gonna be?
I gave it up to Mark. He can either let you guys have the day off, or I said you can do a study session. So he can kind of gauge it. So it's his call. Because we check in, but sometimes it's like, yeah, they're really grooving on this stuff. They don't need a lot of help. Or no, they need a lot of help. Let's do some practice. So it really depends on, I guess, the feedback you give him. If you need it, you can have it. If not, you can start early for break if that works for you. I know you got to go back to Pennsylvania, right? So leaving a few hours early on a Friday might be beneficial, but that's up to Mark.
I gotta take home another guy, so I'm a little bit shaky.
Oh, okay.
Yeah, I was thinking about it.
Leave him behind.
Now that this is getting recorded on time.
Yeah.
Is this considered like second order circuit analysis?
Yeah, because we cannot. So the question is this considered second order circuit analysis? And the answer is yes, because of the 2 right there. Because that says S squared, we have 2 roots and we can't simplify it down to 1 root. Or sometimes we can, but sometimes usually we can't. So that's a second order system. So we can't use that y of t equation anymore. There's no way to combine the L and the C. You can't do any series parallel combinations because they're completely different circuit elements. So you're stuck doing second order circuit analysis. Anything else? Well, don't forget to get started on the homework, right? Because the homework, I don't remember the exact due date, but
Thursday.
do Thursday. Do you want me to push it to next Tuesday? Would that be better, or have it do Thursday?
I would love that. Yeah.
I already submitted it, so it don't
What's
matter.
that?
I already submitted it, so it don't matter to me.
Okay. I think some of your peers are asking for another week, so I'll push that a couple days or 5 days and go from there. All right, before I lose control, have a great day, everybody. I will see you all on Thursday. Take care, everyone.
Thanks. See you then.
Thanks, Paul.
Take care.
Always when a murder. All right.